In this section of the lecture videos, we're going to learn about the buoyant force, and in order to learn about the buoyant force, we're going to discuss Archimedes' principle. Archimedes' principle states that any object that is completely or partially submerged in fluid is buoyed up by a force with magnitude equal to the weight of the fluid displaced by the object. So we're going to say that the buoyant force, which I'm going to use the letter B to stand for buoyant, is equal to the mass of the fluid that has been displaced times g, because we want weight. And by fluid displaced, I want you guys to imagine you filled your bathtub the whole way up to the top, and then you jump in. There's going to be water going everywhere, and the amount of water going everywhere is equal to the amount of the volume of yourself that's actually inside of the tub. Now notice that I said volume instead of mass. Because you have a certain density and the water has a certain density, the mass of the fluid displaced and the mass of yourself that's actually below the surface of the tub and thus displacing the fluid is not going to be the same, but the volume will be the same because you're taking up the same amount of space. And as I said before, the difference is the density and thus the mass. So instead of putting this in terms of mass, we're going to put this in terms of density. So we're going to replace the mass using density equals mass divided by volume with density of the fluid times volume of the fluid displaced, and then we still have g. We can look up the density of the fluid in a table, and it's a lot easier to figure out the volume of the fluid displaced by an object because you can figure out what the volume of the object is. So if you take a square and dunk it below the surface of a fluid, you can get the dimensions of the square or rectangular prism or cube, whatever you want a three-dimensional object you want to use. You can get the dimensions of it and figure out what its volume is. And then you can sink that volume below the surface and you know how much volume of fluid's been displaced. So that means we've now learned how to calculate a new force. So we need to know how to apply that in a Newton's second law type problem. But before we do that, I want to show you guys a simulation to once again emphasize what exactly this buoyant force means. Alright, so now we're going to discuss buoyancy a little bit further using a simulation. So the first thing I want you guys to notice is that there's 100 liters of fluid inside of our container. So I can take this block here and put it in, and notice that the volume has now increased 102 liters. So in order to know how much of the block is submerged, I have to take the 102 liters and subtract off the water that's in the container, so that I would know that there is 2 liters of the block that is submerged. Now, notice here that the pink here is the buoyant force, and the blue here is the force due to gravity on the block, so 2 times 9.8. If I apply an additional force on top in order to push the block further into the water, notice that the amount or volume has increased. So now we are about 4 liters, a little over 4 liters of the block is submerged. And now the buoyant force does not equal the weight of the block anymore. So the buoyant force is actually greater than the weight of the object, so if I now let it go, it goes back up to equilibrium because the water is pushing up on the block. So the more that the block is submerged, the greater the buoyant force. Because remember, the buoyant force is density of the fluid times g times the volume of the object that is below the surface. Alright, so now I want you guys to notice that when it's fully submerged, it has a buoyant force of 49 newtons. Now I'm going to change the density of the object, but not the volume of the object. So I have wood, I'm going to change it into brick. So we have a 5 liters, and notice that the buoyant force is 49 newtons. So despite the fact that I've changed the density of the material, the buoyant force actually hasn't changed, because the buoyant force is calculated by the density of the fluid times 9.8 times the volume of the object that is below the surface of the fluid. So the actual density, I've changed the density from wood, which was 0.4, to brick, which is 2. But my buoyant force, the pink force here, is still 49 newtons because the volume of the object hasn't changed. It isn't until I change the volume of the object that you get a change in the buoyant force. I can also change the buoyant force here by changing the density of the fluid. So if I decrease the density of the fluid, the buoyant force decreases, and if I increase the density of the fluid, the buoyant force increases. So I want to emphasize again that it is the density of the fluid in that equation, not the density of the object. The buoyant force also depends upon how much of the object is below the surface. So you only account for the portion of the object that is below the surface. Alright, so I want to introduce you guys to a couple of scenarios to help you apply buoyant force in a situation where you're summing forces using Newton's second law. So the first scenario we're going to work with is we're going to have an object suspended from a string. And that object is going to be suspended in a container of fluid. Alright, so we want to sum forces on our object suspended from a string inside the fluid. So we're going to have the force due to tension pulling up and the force due to gravity pulling down. And this is what we would have had when we did this in Unit 2. However, now we also have a buoyant force pushing up from the fluid that the object is submerged in. So we're going to have the buoyant force plus the force due to tension minus the force due to gravity equals 0 because the object is at rest. We could then plug in the density, remember this is the density of the fluid, times the volume of the fluid displaced times g plus the force due to tension, and we could plug in m times g, so this is the object, equals 0. Now, this object is fully submerged. And when we're fully submerged, the volume of the fluid displaced is equal to the volume of the object. So we can replace this volume here with the volume of the object. Alright, so now we're going to discuss a second scenario. Now we're going to have something like a raft. They're going to represent a raft with a rectangular prism. So remember, this goes into the page. And we're going to have a box sitting on our raft. And we're going to be in a fluid. Alright, so we're going to sum our forces like before. So we're going to have the weight of the raft, the weight of the box, and then pushing up is going to be the buoyant force. So when we sum our forces, we have the buoyant force minus the weight of the box minus the weight of the raft sums to 0 newtons because this system is at rest. Once again, I'm going to plug in for the buoyant force equation. And I can do mass of the box times g minus mass of the raft times g sums to 0. Now, this time we're not fully submerged. So when we deal with this right here, it's not going to be the volume of the raft because not all of the raft is actually below the surface. We have a subset that is actually below the surface. So we have this volume in here. Remember, this goes into the page. So for a rectangular prism, volume is equal to length times width times height. So length times width here is going to be the surface area of the raft. So that's something you might be given in the problem or something you might be asked to solve for. The height, though, in this formula is going to be the height that's actually below the surface. So the h in this formula is going to be the distance the object is below the surface. So we can replace this volume with the area, so that's essentially the rectangle that makes up the top or the bottom of the raft, specifically the bottom here, times the height, which is the distance below the surface that the raft is sitting, times g. And then we have mass of the box times g minus mass of the raft times g equals 0 newtons. Now there's one other thing I want to point out in here. We've been using mass of the object, and traditionally that is what you would be given in the problem. However, remember that mass is equal to density times volume. So even if you're given the volume of the object, if you're given the density table, you can solve for the mass. So that is an option you can use as well. The last thing I want to talk about is why do objects sink or float. So I'm going to take my object once again and put it in a container of fluid. So now when we sum forces, we have the weight of the object down and the buoyant force pushing up. So we had the buoyant force minus the weight. This time though, we don't know if it is in equilibrium. So I'm going to sub in here density of the fluid displaced times, not fluid displaced, just the fluid, times the volume of the fluid displaced times g minus mass of the object times g equals mass of the object times the acceleration in the y direction. Now this is fully submerged, so I have the option now of making this the volume of the object. And this time I'm going to replace the mass of the object with the density of the object times the volume of the object. Now you notice volume of the object in g and volume of the object in g in both of these terms, so I'm going to factor them out so that we can focus in on the densities. So we have a subtraction here between the two densities, density of the fluid and density of the object. So when density of the fluid is greater than the density of the object, that subtraction will be positive, thus making the right-hand side of the equation be positive. So you have acceleration in the positive y direction, so the object will float. If density of the fluid is less than density of the object, though, when you do the subtraction, you get a negative answer, so your acceleration ends up being negative, and the object will sink. So the buoyant force explains why density matters when objects sink or float in a fluid.